Hey, thanks everyone for coming. I know it's like a tough hour in the morning and everything to hear something a bit more intense than usual. I'm really excited to speak here at AltConf after many years of attending AltConf and WWDC, so moving to the speaker area is an interesting change. So, yeah. A bit about myself. So I've been an iOS developer for the past 9 years. I've been working also with complementary technologies such as React Native, Rails, and Node.js on the back end. I'm one of the lead developers for iOS in Applicaster, and I lead the dev relations as well. So I'm in charge with working both with external and internal developers on our technologies. A bit about Applicaster. So we're trying to solve basically two main problems. Make the distance between the app manager and the user shorter and enable development teams to move fast. We're doing that by our own homegrown CMS called Zap, which is an app management and development platform, which enables us basically to configure everything remotely as much as possible and then generate builds. And we basically bring whatever other third-party functionalities to our system by a marketplace of plugins. But let's talk a bit about crashes. So we all get them, basically, and they're not very fun. And I'm here to basically try to give you today a few more tools in your tool belt to deal with them. I'm going to focus on three main topics today. First one is common crashes we encounter, how we can try and debug them quickly and try to understand like what's going on. The second one, how do crash log looks, what they are, how to read them, and a few small tips about symbolicating them for those tough cases where they don't appear very understandable for us. And the last thing is some best practices about gathering crashes. So literally the know-how and how to move from just collecting crash logs on a device to the next levels, basically. But before delving into the common crashes, I want to point out a bit about the talk today. What our goals are. I think it's a good place to start with. So we're going to try to identify the line in the code that causes the crash. That's basically the best case scenario we can get to. If not, let's at least understand the reason that the code crashed. And if we cannot do that, let's get to the shortest stack that we can of understandable, readable commands in the crash log. So each one of the tips I'm going to go and methods, basically that's the aim. Let's try to be more informed, basically, about what we're seeing. A bit about the examples I'm going to show today. So I'm going to show code snippets on the screen, and we have a demo project on GitHub to play with. But I want you guys to be in some context. So this is going to be very simple. Okay, most crashes will be caused by 2-3 lines of code. Okay, there'll be no networking code, no async code, because that's kind of, I don't want to try to do networking here. I learned from Apple yesterday. Doesn't always go that well. And also, there are no dependencies, open source, or precompiled libraries. Now, that part, obviously in real life, that's not always the case. And that always complicates, especially when you work with closed libraries or big open source code that isn't ours. So all those tools that I'm going to show today become even more powerful in those real life scenarios. Let's start with some very common reasons for crashes to happen. So the top 3 that I picked to talk about today are the following. Unrecognized selector, so basically trying to call a function that doesn't exist on an object. Bad memory access, usually but not exclusively trying to access an object in memory and getting some garbage as a result. And the third one is watchdog crashes. Those are a bit less common, but they're usually caused by significant memory leaks or fast allocations of memory. And it's important to know how they differ, because they look very different from regular crash logs. So even though they might not be that common, it's worth looking at them just to know how to identify them. Now, obviously, there are many more reasons to crash, yeah? Out of bounds, force unwrapping, etc. I just picked those 3 as they're very common, and Xcode doesn't necessarily do a great job in explaining us or showing us how to redeem ourselves from that point. So like I said, I posted the slides in the code at github.com/applicaster/altconf19, 2019. Basically, the entire project is there. The slides are there, so feel free basically afterwards to download it and play with it It's just basically a couple of buttons, one after the other, each one causing another type of crash. So the first family of crashes I'm going to talk about today is unrecognized selector sent to instance. It happens when a function usually is called on a class or an object that doesn't implement them. It's super common in Objective-C, obviously, because especially when you're passing NS objects around or getting all kind of casting of networks, it's dictionary and what's the next key inside and stuff like that. But it can also happen in Swift. Yeah, obviously, just don't force unwrap, and it will help you a lot. It will go a long way for that, but it can happen there too. So let's look directly at the example. Okay, this log, if you can see more or less, the reason for the crash is basically there's a crash with NSCF string that's getting called a function count by enumerating with state objects count. Great, not so great. I'll also delve about how we see exactly what ran, what thread, and so on. But basically, this crashes on the main thread. And actually, if you look at line number 5, it's kind of easy to understand exactly what happened. The code is symbolicated. Everything looks great. Like if you put a couple of minutes in it, you might assume, yeah, everything's good. But this is a very, very, very optimistic scenario. This is why I said examples are going to be simple. But if we try to look at the bigger picture, we just run it in Xcode and we let it crash, you'll notice that the place where it stops is basically the main function. And that's not very helpful, right? Especially if it was like a bigger code base and not our library, this would have been way less useful. A thing that I like to do is always start with the documentation, because basically you have the class and you have the method that is not implemented there, and sometimes those methods are basically Apple methods. So looking at them and looking at the documentation really helps, like stepping back and having like some context. So in this case, this is a fast enumeration method. So most likely we had a string, we expected an enumerable object like an array or something like that, and here we go. Our first line of defense is, of course, breakpoints. So there are basically two types of breakpoints that are always a good starting point to go with. The first one is the Swift error breakpoint that covers all the common Swift errors and exceptions. And the other one is the general exception breakpoint. Now, a bit about the general exception breakpoint. It stops a lot of scenarios, basically, especially in C++ and around some of the background frameworks that Apple has. So if you try to do that with Mediafile and stuff like that, you'll notice it will break you a lot of times without crashing. So you'll just like hit play, just to continue, and it will continue. So I do suggest turning it to Objective-C. That removes a lot of the white noise and makes you able to move forward. Adding breakpoints, I hope that everybody knows, but at the bottom left, there's a plus sign at the breakpoint navigator, and you can add those basically built-in breakpoints. Now, if we try the same scenario basically with the breakpoint, we see we're in a much better state. So suddenly we know exactly in the app what happened. The app didn't crash. And more importantly than that, we're able to print objects in the context. So since we're not like basically after the effect, but before the effect, you can really get like a good understanding of what's going on. Now the question is this enough? Is this the happy ending we wanted? Well, sometimes. If the crash is directly in our code, the answer is yes. This is probably where we would stop, and that would be enough. But the problem is where it's called functions that we cannot find, or it crashes not in our code, in a background thread, and so on. So we try to go the one step beyond. So let's look on how we do that. So the best way to do that is basically to have a breakpoint on that function that does not exist. There are two ways to do that. The first one is symbolic breakpoints and extensions. For symbolic breakpoints, also from the breakpoint navigator, you hit plus, you choose a symbolic breakpoint, and you can usually copy-paste the debugger message for unrecognized selector sent to instance, copy it into the symbolic breakpoint, and run it. I gotta say, it works most of the time. Yeah, I did encounter cases where it doesn't work, and when it doesn't work and you gotta play with that syntax, it's starting to be a bit annoying. The second method that is a bit more hacky, but it's extremely powerful, is basically adding an extension. So basically, since you know the class you're going to look at, you also know the function that it crashes on. You can basically implement the function, put a breakpoint in that function, and then you're basically stopped with the call on the object. This allows you to not only print the object, see the context, maybe try to understand where it was called from with a shorter stack, because breakpoints always stops in shorter stacks than crashes. But this also gives you, first of all, for debugging, you can basically do some behavior and the app won't crash. I'm not sure you would like that, but in case you have to work, with some third party that is not going to update their third party and your scenario exactly crashes, you can basically mitigate that. Expect another object, do another behavior, just continue onwards and so on. Yeah, I really wouldn't recommend putting it basically in production code though, because this extension then goes basically all over and you might do things that you're not expecting to do. Let's say if someone suddenly checks if your object implements a certain call, then it suddenly does implement it. So has a lot of meanings of ramifications to do, but it's a very powerful tool and it's an amazing debugging tool. And basically, this is the outcome of our work. So when we run it, we can see the object, the context, we can print the objects, we can avoid crashing at all. Wrapping up on recognized selectors. So first of all, we found out how to go about them. What do they mean, how to read them, and how one of those crash logs looks. The second one is we learned how to improve the stack trace and shorten it as much as possible through the use of breakpoints. And the third thing is basically we have a couple of new tricks of knowing how to mitigate those breakpoints if we have to. The next issue I'm going to talk about is bad memory access. I'm going to focus specifically on a family of those. So trying to access released objects, basically dangling pointers. So we see a crash log here. In this case, the exception is exec bad access. I think almost everybody that developed like more than a month on iOS have seen those, and they're not very helpful. And this example, Xcode, actually stops in the correct place again. But this is, and just reading the code makes it kind of apparent of what happened here, okay? But this was caused, a few lines up. So if you see, you can see where it crashed, but the cause is above that, and the crash itself didn't cause like anything. This project basically passes with no warnings, no exceptions, no nothing like that. Yeah, didn't do any tricks. And if it was 5 functions up in a different thread, it's like kind of good luck of understanding what's going on. And if it's not in your code, it will be also very hard to understand the context. So we want to understand what happened, and we have a first line of defense here. Apple actually gives us, and it's called zombies. Basically, just to understand how to activate zombies, let's start with that. So you go to the app target, edit scheme, run diagnostic, memory management, zombies object. So a bit about zombies and memory management. We got to take a step back and kind of talk 2 seconds about memory management in Objective-C in iOS. So each object has a reference count property, which is the number of objects basically pointing to it. When no more objects are pointing to that, the reference count drops to 0, and the object is released. When trying to access such a released object, in many cases, we will get a crash since that memory might have been reused, it doesn't contain some of the information about the object, and so on. Now, a very common place where this might happen, basically, is when you have delegates and you're passing them around and saving them, suddenly that delegate is released and you're calling it. Even in Apple frameworks, I found that in many cases, even though the header will say weak, or even third parties, actually it's a sign behind the scenes. And then you think you're safe, because weak then can be nil safely once they're released, but not always the case. So what does this DomB Flag do? So I think it's important to understand what the tools that we're using are doing actually behind the scene, and not just mark it and forget about it. basically, what it does, it keeps the objects in memory, and whenever someone tries to send a message to one of those objects, it makes an assertion. And that assertions come with all the context, basically. Obviously, due to the nature of this behavior, this will cause very high memory usage, because basically you're mostly not letting objects be released. So be aware of that, and obviously do not turn it on by default when you're debugging. Not because it won't show you more, but because you'll be losing a couple of things, such as, for example, in the profiler, you won't be able to see anything that has to do with memory behavior because you're suddenly not deallocating stuff. And on big projects, it's not fun when suddenly a project takes 4 gigs of your memory. But it really helps to flush out those potential scenarios. And the reason I say flush out, because in many cases, this will catch that behavior way earlier than you expect. So you might think you have a problem only when you get to the bad access, but actually other cases where they might have happened earlier, this helps flush them out. So if we turn that flag and we run the project again, we see that this time it stops again, but we have an additional, basically, debugger message. And it's slightly more informative. We know the type of object, we know the message that was sent to it, and not only something very generic, and we have the memory address. Now, I'm not gonna go into how to use memory addresses then to start printing the objects. There's a great DomB talk about that from last year, and I'm gonna point it out basically in one of the following slides. Another way to get the same information but kind of have a more drilled down view on that is basically using the instrument. So you have a zombie's profile there, and if you run it, it will basically alert you when a zombie happened, and you can look at the stack and you can see basically the things that led into that and so on. Now, if we're wrapping up memory and bad memory access, so we basically were able to identify a very common crash, understand how it looks, and specifically how to address accessing released objects. We know now basically how to make sure this happened because of that, because we're able to turn the zombie flag on and to see that that was actually the culprit in this case, and it's not just a different bad memory access issue. And we basically improved our knowledge on what is happening with the issue, because now we're able to know what's the object type, what's the message, and what's the memory address. And this basically, it might be enough in some cases, but this is a portal basically to taking it to the next level if you want to delve that deep, sorry. Now let's get to the last family of crashes I'm going to talk about today. Those crashes are trigger a generic non-app specific log, and this is basically the hard part about that. So if you look at the log at the right, you'll see that the log is not app specific. It no longer says like AltConf1, which was the app it was run from. It says unknown log. Turns out that many actions that the user can take, or better said, we let the user to take, will trigger non-app specific crash logs that looks like this. The type of crash is sometimes very baffling. I read through it even for myself. Knowing those crashes, I would look through it, and I cannot tell you, unless I start reading about each field, about what was the reason. And usually 90% of the time, the app crashes while the user uses it, and it's due to fast memory allocations. There are all kinds of behaviors that trigger the watchdog to kill the app, basically. There are many cases of things you got to report to Apple. There are many cases of fast allocation. There are many cases of you're using too much CPU, not giving enough time to the main thread for the user to catch the clicks and stuff like that. And those, in many cases, render those type of unknown logs. In this case, basically, the app will crash, and it will not generate the crash log that will come to you. So even if you're acting very responsibly, you look at iTunes every day to see in Xcode and the iTunes logs, you won't see it. You look at, you have something like Hockey app or Crashlytics connected to it, you won't see it. And only if you take the device literally and try to understand what happened, you'll see this unknown log. So the hard part is actually understanding what happened, because it doesn't reproduce on the simulator. The reason is the simulator runs basically off your Mac resources. You have a lot more memory, you You have a lot more CPU cores and stuff like that. And on top of that, basically the watchdog behavior, since you're running as a native process on your Mac, just doesn't behave the same and doesn't kill it. So there are two very, very basic tools that you can look at that will give you like a good bird's eye view of those issues usually. In the Xcode itself, basically you can look at the current debug session and you can see a couple of parameters. They actually added a couple of more parameters this year. But you can see basically the memory usage, and you can see the graph of how it behaves, and you can see also the CPU. Those are two very good indicators that if you start going, to 99%, in this case it's one core, yeah, or you start seeing like a sharp memory graph, and your app dies on devices, that would be a good place to start. You'll notice that on the top right, it's a bit cut in the slides, but we have a profile and instruments button. And let's quickly look at those two. So if you hit those, you basically are transferred to an instrument session that's already set up with the proper tooling for you. In fact, that session, it's pretty cool that if you have some configurations, you can actually transfer whatever you started doing in the simulator before in Xcode. You can transfer it directly into instruments and continue debugging that case then. If we look quickly at this example, basically hit consume memory in the demo just to reproduce it. You can see that tracing the memory allocations is actually pretty easy. You can then mark in instruments basically a segment, a time from a certain action or from a certain timestamp to a timestamp and see the memory allocations. And then when you look at those, it's kind of easy to see that the same thing repeats or the size of the allocations that basically happened with each action. The CPU example is kind of the same. In this case, it's also, you can select like a certain time and drill down all the way down and see the type of functions that took the most time. And it's really easy basically to hunker down on the culprit in this case and understand what was going on. So wrapping up watchdog crashes. Just be aware that they exist. They don't produce standard crash logs, and they might be a bit trickier to gather from the users. But in case you have also like internal feedback or external feedback that the app dies and you don't see anything that correlates to that, just taking a device that might have had the crash or trying to reproduce it and be aware like of the instrument state, that might go a long way, especially on weaker devices, on older devices. This is way more common. Each device has basically its own limits. Okay, so if you're running on a phone with 256 megs, I'm not sure if those are supported anymore actually. You'll get there really fast if you try, for example, to open a few images, turns them to bitmaps, and see. But if you're working, on a nice iPad Pro, might not encounter that. So be aware of those crashes. Be aware that they might not generate the standard crash logs and might not trigger the usual alerts that you're used to seeing. Don't try to reproduce those issues on your Mac. I know it's very tempting. It's way more comfortable to just run the simulator and have fun with it. If we could all develop only in the simulator, I think that it would have saved us a lot of time. But this is one of those classic scenarios where running it in the simulator, you just won't be able to see it most likely. You have so much more memory and so much more resources, and nothing kills your app. You can go crazy. If you run actually that demo project on your computer, you'll see it can go to 16 gigs of memory. It can start eating your virtual memory. And, the OS is like, fine, okay, you might be doing, I don't know, rocket science or something like that and not just a straight up bug. And the third thing is basically monitoring the Xcode session debugging. Just, keep a look on it from time to time. It gives you a very good indication of, when you're leaking memory. It gives you a very good indication of where you have suddenly crazy allocations, and kind of look at it that it makes sense. So that's it. Before moving on and talking about the anatomy of crash logs, I'll try to give a few good practices to handle crashes in general. So first of all, use the general breakpoints. They're very useful. The Objective-C and the Swift breakpoints, as I showed in the previous slide, will help you catch a lot of issues. And in many cases, it does like a really good job about where's the issue, what's the reason for the crash, might not offer you the entire solution, but it will get you there. The second thing is use Swift, and use Swift with optionals. Use Swift with optionals, and don't do force unwrapping. I find in many cases, we're kind of lazy. It's the end of the day. I want to ship that code. I'm going to hit a bang there, and I'm going to send it to production. No pull request needed. But it's not a good idea. And once you go basically to Swift with optionals and you do all the unwrapping safely with optionals and all your classes, especially if you start migrating those classes from Objective-C to Swift, or you add the optional, it really solves a lot of issues. And my third tip of the day basically will be get familiar with instruments and look at the WWDC talks. Especially, there are two talks I'm pointing out here, one from 2014, one of 2018. The talk, they're basically called the same, Understanding Crashes and Crash Logs. They have like different points in each one of them and different tricks. They're very useful to look at. And there's also the Apple Tech Note, which is super detailed, and for some reason they say it's no longer maintained, but it seems to be maintained, and there's no replacement, and they're still pointing to it from everywhere. That Apple Note is also super technical, super informative, and gives a lot of insight, basically about the crash logs, how to use them, and how to read them. Now let's talk about the crash logs themselves, how they look, and what are the main sections. So I kind of broke it down into sections. I should have done a better job annotating on that, but I'll start reading and telling you a bit about the sections and what's the focus of each section. So the first section basically contains basic information such as the hardware, the process that caused the crash, the bundle identifier version, general information like that. The second one contains the time and the OS version. And the time, you have two fields there, which are very important in many cases. One of them when the app was launched, and the other one when the app crashed. Especially you see on launch crashes, that time is very short, but you can kind of understand if it's something that takes a second or it's somewhere down the user path. The third section is the actual exception type, the memory information and the termination code. So exit 0, exit 1, obviously not exit 0, but the different termination code that are different from 0. Now, a very important segment in that one is basically the thread that crashes. Okay, so the last line of the third segment has basically the thread that crashes. In this case, it's 0, which represents the main thread, the UI thread. But any other number basically usually represents a different thread. And it's important later when you read through the crash stack to know which one of the threads is the relevant one to look at. The fourth section basically contains the stack trace itself. Each thread basically has its own stack trace, and it shows basically the last commands that were ran just before the crash. Now, it's not shown here, but if you scroll all the way down after everything, you would see basically a map of exactly which libraries are loaded. So there's like a binary map, tells you exactly which versions of the libraries where they were taken from. And sometimes it's useful, especially if the crash is another type of crash I didn't talk about today, which are symbols, binary symbols that were not found through the runtime but were expected. That's basically your first line of defense of understanding, wait, was my library actually loaded or not? Now, the problem starts with Xcode when the console app doesn't really symbolicate. So you might be getting a crash from someone in the mail. You might be connecting the device, and you might not have the project. It might not add the symbols automatically, and then it looks kind of grim, because if you look on the left side, you basically cannot get any useful information. If you look on the right side, you see a crash log, and you might understand what went there, how to go about for reproducing it. Now, if you saved either the binary, okay, so it's a symbol-rich binary, which they started setting as default lately, or if you have the dsym folder, which, by the way, notice that when you use a lot of development SDKs and you compile them, basically make sure to save those dsym folders as well, because they actually mean, because this will be the dsym folder for the app, but not necessarily for the dependencies. Kind of depends on how you chain everything together. then you're in luck. Also, you can sometimes download the DSIM from iTunes Connect through Xcode, and then you're basically golden. As a side note, local archives also usually save all the symbols and should usually be used to automatically desymbolicate them. But in those cases where the magic doesn't happen and you're still looking like at a blank crash log, but you think you might have the relevant DSIM or the binary that was used basically in that case, there is a way to symbolicate it manually. I'll say already, there are a couple of ways. So the technical notes shows another way, but this is the way that I'm used to maybe historically using, and it's super powerful, super straightforward. So basically, it starts with a new annoying step, which is you got to export the developer directory from inside Xcode. So I'm not sure if you see it there so great, but download the slides, because I guess if you get to this level, you should. Then you run the symbolicate crash command from its location. So basically, it's some location inside of the Xcode app, content, shared framework, DVT foundation, framework, and so on. When the first parameter is the crash log, the second parameter could be either the app binary or the desymbolication directory, and you can either add -o at the end or just pipe it into a file, or it will just literally print the entire crash log into the bash command, zsh now. There are a couple of more methods, but this is just really straightforward. I like using command line tools. It's always there. It's always in Xcode, so you don't have to jump to too many hooks to get it running. Let's talk a bit about collecting those crash logs. So there are 3 main methods to do that. If you have access to a device, then great. You basically take the device and you'll connect it. I'll show it in a minute. You can go to see production crash logs through Xcode. It grabs it from iTunes Connect for you. And the third one is basically use all kind of SDKs and services that give crash log collecting. And let's talk a bit about all of those options. So to grab a crash log of a device, you basically take the device, you connect it to the USB and unlock it, open the Xcode, hit Command-Shift-2, which is the device and simulator pane, and click the view device logs. Now, give it a couple of minutes, especially if it's a new device that you never connected. It takes it a couple of minutes just to grab all the crash logs, try to symbolicate, populate the table, do sleep 100 in repeat. Yeah, I don't really know why it sometimes takes so much time, but be patient with it. Give it a few minutes, and then do open logs again, and you will probably see your crash log. To grab crash logs from iTunes Connect, basically, it used to be in iTunes Connect, and it kind of moved around. Now it's in Xcode. First thing that you got to know is make sure basically Xcode knows about your iTunes Connect Developer Center user. Now it's the same thing finally. So go to the preferences, accounts, and make sure you log in to the relevant account or accounts. Kind of depends on what's your workflow. So basically this enables us to get to step number 2, which is open the window organizer. And then on the left, you would see basically a list of all your apps. You can choose them. Then you choose the correct version. You go to the crash area. You choose the correct version. Make sure you're looking at either whatever test flight that people complained about, or about the store version. Like if you don't do that, it just chooses the latest build, and you'll see no crashes. And people are surprised, why are my crashes? But yeah, they are actually happening. And then basically it will show you a list of crashes. Those lists of crashes will come with how many devices they affected. If you go into each one of them, you'll get some statistics, which devices it happened more, all kind of information like that. The problem with this is basically, from what I saw, they changed the behavior and you're not getting the entire crash log. You basically get the 5 example stacks, which might be a bit annoying, might be a bit enough information there, especially when it comes symbolicated, but it's not great. And you do have a button which basically allows you to open in project, which is really cool. But this is not a full crash history. This is the last couple of weeks, and they might be missing some things. I've seen it basically missing issues entirely. But it's a good starting point, especially if you have like, you want to put into your workflow one step to monitor all your apps quickly, go one after the other, see what's going on in the last 2 weeks, be up to date. This is a nice way to start with. But if you want to go beyond that, it's time to talk about basically third-party crash collecting services. So there are a couple of very known ones that most of the people use, like HockeyApp, Crashlytics, Instabug. And most of those SDKs are really easy to integrate. Basically, you usually initialize them, give them an identifier at the beginning, and you kind of forget about it and let them do their own magic in the backend. And from that point onwards, with that identifier, they will upload the crash logs automatically on the next launch. Okay, so if something crashes one after the other really fast, you're better looking at iTunes than at those. But if the app actually launches the next time, you'll be getting it uploaded then. And most of those services also arrange them, Symbolicate them, and so on. For the best performance, obviously, you have to put into your flow also uploading the binary, either the symbol-rich binary, the DSym, or at best case, you upload both of them. And then they do all the automatic symbolication, and it gives them way more insights, and then it gives you way more insights when you look at those common crash logs. And the good thing is basically, it gives you daily mails. You can see like larger statistics over time, compare versions and stuff like that. So I really suggest working with one of those. It's like, if you want to be serious about crash logs and monitoring, and you have a lot of apps and you want to see trends over time, this is basically, I think, the only way to go around it. And just to sum up what we learned today, so we talked about common crashes, how crash log looks, and how to collect them. Hope this talk has been beneficial for the people that came here this morning. You can go get the slides and the demo projects at github.com/applicator/AltConf 2019. And have fun with it, make changes, get new crashes. Yeah, I don't know if we have any time for questions, but so maybe like 1 or 2 questions if anybody has, and if not, I'll stay here after the talk. I'll be glad to delve into whatever you guys want. Okay, so we're always hiring. I think like most companies here say that, and we have multiple locations around the world. So we are from Israel, from London, from New York, from San Jose, from Miami. So if what we're doing sounds interesting to you, I'll be glad you can go and check our career sites. And also I talked about the plugin marketplace. So if you guys are working on products around media apps, we're always interested to learn about them and to meet people, and you can drop me a line. This is my mail, so I'll try to leave it a couple of minutes after the talk. Yeah. And thank you, everybody, for coming.